So today we'll be going over the method of undetermined coefficients, and this is specifically used to solve non-homogeneous differential equations. So up to this point, we've been going over different methods on how to solve homogeneous differential equations. But what happens when you have a non-homogeneous differential equation? Well, let's look at an example first. So let's say we have a differential equation such as this: y double prime plus 4y prime take away 2y is equal to 0. So of course, this is a homogeneous differential equation, but what if we're dealing with a non-homogeneous differential equation? In other words, this is equal to some function g of x. So the general way to solve a non-homogeneous differential equation is to first basically assume that it's a homogeneous equation first, and that's where you find the general solution, which we've dealt with methods in the previous videos. And so we get the solution to the homogeneous function first, right? So we just call it y of h, the solution to the homogeneous differential equation. And then afterwards, we find what we call the particular solution in this case, which is nothing more than the solution to the non-homogeneous differential equation, which we'll be going over, which is the method of undetermined coefficients. So once we have the particular solution, which is the solution of the non-homogeneous differential equation, as well as the solution of the homogeneous equation, then the general solution of that differential equation is the linear combination of the homogeneous plus the particular solution. Just like the previous video of linearly independent solutions, the general solution will be a linear combination of the two, the homogeneous and the particular solution. So let's go ahead and let's look at the method of undetermined coefficients to be able to solve non-homogeneous differential equations. So for the first example, we have this non-homogeneous differential equation: y double prime plus 4y prime take away 2y is equal to 2x squared take away 3x plus 6. So this side, your right side, would be that g of x that we see, which makes it non-homogeneous since it's not equal to 0. And so the first step here would be to solve the homogeneous differential equation. So we have the differential equation, we equal it to 0 because we're first solving the homogeneous part of it, and we see that this is it has constant coefficients. So we're able to get the characteristic or the auxiliary equation for this differential equation. So we have r squared plus 4r take away 2 is equal to 0. Now solving for the roots, we have, using the quadratic formula, we get this, and so the roots would be -2 plus or minus the square root of 6. So the homogeneous solution is the arbitrary constant c1 times e to the power of -2 plus square root of 6 plus c2 e to the power of -2 minus square root 6. So this is how the homogeneous solution. So just one quick thing to note, I actually forgot the x variable here when solving the homogeneous solution, just so I won't confuse you guys. But yeah. And now the second step is going to get the particular solution. So just remember, the particular solution is what the solution to the non-homogeneous differential equation is. So it's just that. That's what we call the particular solution. So just to rewrite the non-homogeneous differential equation right here, now the second step would be just focusing on the right-hand side, or that g of x. So we're supposed to look at the family of this function. Now, what exactly does that mean? So a family of a function, in this case g of x, is a set of all linearly independent functions of which g of x and all of its derivatives are linear combinations. So essentially, let's look at an example here. So let's say for the first function you have x to the power n, where n could be any number 1, 2, 3, and so forth. So for the first family, of course, it's going to be x to the power of n. Now, what would be the next family of this? Well, the derivative in that case would be the x to the power of n minus 1. In this case, you don't need to consider the coefficient because we're looking at the family of it, right? It could be multiplied by any multiple or any coefficient regardless. And of course, the derivative of that is you keep on going and so forth, x to the power of n take away 2 until you keep on going to the derivative. Sooner or later, you'll end up with 1. So these are all the families of that function x to the power of n. So let's say for our next function, we have e to the power ax. Well, if you keep on getting the derivatives, you would always get e to the power of ax. Of course, the coefficients would be changing, but it would still be e to the power of ax. It'll be a multiple of that. So the only family for the function e to the power of ax is itself, right? So how about this function? If we have sine alpha x, well, the first family would be obvious, right? Sine alpha x. If we get the derivative, it'll be cosine alpha x. But what if we get the derivative of cosine alpha x? Of course, it'll be negative sine alpha x. But since it's just a multiple of this, it's already included in the family. So the family of sine alpha x is just sine and cosine alpha x. So how about this last one, cosine alpha x? So the first family of this function is, of course, cosine alpha x. You get the derivative, it will be negative sine alpha x, but the negative is just a multiple of sine alpha x. So these would be the families of this function. So hopefully you guys start understanding the concept of what it means to find the families of a function. So let's go back to the what we were solving for the particular solution. So what are the families of this function? 2x squared take away 3x plus 6. So for the first one, we see x squared. So that will be the first family that we have. X squared, multiples of that. Let's go ahead and put this in parentheses. Once you get the derivative, it's going to be x, multiples of x. You get the derivative and you finally end up with 1. Now, luckily enough, even this one, the families would be x. We have that already included in the first in we already have it included. And for the 6, it'll just be a constant, which will be a multiple of 1 here. So these are the families of the function. Now, once we determine all the families of the function, this is where we get the particular solution, what we call the particular solution, which is going to be the families multiplied by a constant. And we could call these constants just by any arbitrary variable. For let's say for the first one, constant a times one of the families plus the constant b times the second family of the function plus c. And then this is where you get the derivatives of the particular solution as well as the second derivative of the particular solution. And then with these derivatives, what you do is go ahead and plug all this back into the differential equation and you solve for the variables a, b, and c. So we have the derivatives here and then you plug it in back to the differential equation to solve for a, b, and c. So going back to the non-homogeneous differential equation here, since we have the second derivative, first derivative, as well as the function y, we plug it in here and then solve for the variables a, b, and c. So after plugging it in, you have 2a plus 8ax plus 4b take away 2ax squared take away 2bx take away 2c is equal to 2x squared take away 3x plus 6. Now this is where you simplify by basically distribution, right? Whenever you're able to distribute out like a x or a x squared, you're able to simplify the equation a little bit more. So this is exactly what we're going to be doing here. So first, I basically changed some things around. I started with x squared, so negative 2a x squared plus, in parentheses, 8a take away 2b, factored out the x to simplify, plus 2a plus 4b take away 2c. So these are your constants. Now, since this is equal to 2x squared take away 3x plus 6, you see that the coefficient of x squared here and this are equal to each other, right? Since we're solving for the variables a, b, and c, we see that negative 2a is going to be equal to a coefficient of whatever it is for the x squared on either side. So negative 2a is equal to 2, and you just solve for a, right? We see that a is equal to negative 1 in this case. And let's see for the variable x, we have 8a take away 2b is equal to negative 3 here. So let me write that. So 8a take away 2b is equal to negative 3. Then we already have the value of a, which is negative 1. Then we go ahead and solve for b, which is equal to negative 5 halves. Now let's go ahead to the other one, which are these constants is equal to this constant here. So let's go ahead and write that. Since we already have the values of a and b, we just solve for c, and c ends up being equal to negative 9. So since initially we got the particular solution with the variables a, b, and c, and we solved it, the particular solution ends up being negative x squared, take away 5 halves x, take away 9. Remember, these were the variables a, this was b, and this was c, which we solved for. Now, since we already have the homogeneous and the particular solution, then the general solution would be just a linear combination of the two. So just adding them up gives you the general solution. So once you plug it in, add them together, this is your general solution to the non-homogeneous differential equation. And this is the method of undetermined coefficients, basically finding the families of the function g of x and solving for the appropriate variables that we named a, b, and c and such. This is the method used to solve non-homogeneous differential equations. So first step, solving gain the solution to the homogeneous differential equation. Your second step is finding the particular solution by gain the families of the function g of x, and then you solve, and the general solution will be the linear combination of both the homogeneous and the particular solution.